texture features are going to consider not only the absolute values of the pixels, but also the relationships between pixel values within some region. That means a given color that is found in a flat region will differ from the same color but now found in a region with high variance. The idea of describing texture is to differentiate between patterns of pixel variances and then codify in some way the texture behavior. There are many texture descriptors in the literature, but in this notebook I will focus on the LBP as implemented in scikit image package. As we discussed in the previous video, texture has semantics that explain the way elements relate to each other visually, and then also can relate to the behavior of that scene and patterns of such as interlaced, sprinkled, braided, bubbly, dotted, checkered. So those are just 6 examples, but are many of them. You can think about the way we describe texture. And in this notebook, I'm going to describe those and try to differentiate them, compare them using the LBP codes. Local binary patterns and methods that are variants of this are efficient as a descriptor for texture analysis. I explained that in the previous video, so I'm not going to go into detail, but there are something that I want to emphasize here. So when we define the number of points that we are going to sample around the central pixel, those sampled points will become the LBP code. In the case of 8 sampled pixels in a neighborhood, we have 256 unique codes that can be associated with local shape patterns. For example, those 2 first patterns here, composed of only zeros and ones, are related to flat regions, while those 2 other ones here are related to edge and corners. And there are the ones that are called non-uniform because they have more than 2 transitions between zeros and ones. However, in scikit image, uniform are also those that are rotation invariant codes. That means that in edge that it is represented as, for example, 4 zeros followed by 4 ones is considered to be the same as 2 zeros followed by 4 ones and 2 zeros. Note that this is only a code that it was rotated with respect to this one. So in scikit image, when we the implementation, we will assign those 2 codes to the same bin. Therefore, with 8 points, we have 10 bins representing 9 bins for rotation invariant uniform codes and 1 bin for all other non-uniform codes. In my implementation of this function, LBP features, we may define the radius, which defines the distance between the central pixel and the sampling pixels, and the number of sampling pixels. The default would be 1 and 8. If a RGB image is provided, we have to convert it to grayscale in a single channel. I also convert it to unsigned int 8 for guarantee that we have the correct number of gray levels. I also choose to normalize the values using min-max normalization, and then compute the LBP provided by the scikit image package. However, this function will return a matrix with the codes, so we can now compute the descriptor using the histogram of the lbp.revel. Note that the number of values will be related to the number of sampling pixels. So as I told you, in this case, in 8 points we have 10 bins. With p points we are going to have p plus 2 bins. I'm also going to normalize the histogram and return it. And I'm going to use the Euclidean distance in order to compare those vectors. So I loaded some texture images, and then I computed the features between of all of them. For all of them, I considered a radius of 2 and 8 points, but you could change that if you want. And then I computed the Euclidean distance between the first image that I'm going to use as a query image and all of the remaining ones. Note here that the first image has the same texture of the second and third images. And then we have also 3 other textures that are different, but well, we can check how similar they are with the with respect to the first one. So in here I just correct from Portuguese to English. So it's the query image, and the remaining ones define the rank. That means the images that are close to the query. So by using the LBP descriptor, this is the query image, and then the rank 1 image is this one, the rank 2. So this number here is the Euclidean distance between that image and the query image, considering the LBP descriptor. Note how this distance increases as we move to other textures that are dissimilar to the query. And I also can plot the actual histogram of the LBP descriptor to note visually what is the difference between the LBP codes. As you can see here, the query and rank 1 and rank 2 images looks quite similar in terms of the distribution. When we look at the rank 3, is also similar, but not as much as the other ones. Probably this third code here was found to be was more present, and the fourth one was not that present. So this probably is the case that why it appears in rank 3. But for rank 4 and 5, those are very dissimilar to the first one. So the LBP can be effectively used for texture analysis, but also should suggest you to implement and test the gray level co-occurrence matrices with hierarchic descriptors as well.